A classical particle is confined to a one-dimensional line segment. When we give it initial momentum, it bounces back and forth between the walls, always obeying Newton's laws. Let's also confine a quantum particle to a similar 1D box. I represent its wave function by this rainbow-colored object, and I represent its complex components by these monochromatic shapes. This is an artistic quantum render. Even though there will be portions of this video that are geared towards those with some quantum mechanical background, even if you have no mathematical background whatsoever, I assure you, you will at least be able to appreciate the mathematical beauty. I promise not to throw any equations at you. You will only observe the evolution of geometric shapes as the simulation unfolds. We will soon unleash this wave packet and evolve it under the Schrödinger equation. Will this quantum particle bounce around like its classical counterpart? Let's see. The packet follows the classical trajectory as it travels and bounces. The wave function spreads out and covers the entire line segment. Eventually, the wave packet shape is lost. Its position can no longer be approximated classically. Focus on the central structure representing the entire wave function psi. The cylindrical radius is psi's amplitude, and the hue is psi's complex phase. The surrounding structures represent complex components. I take the real component of psi and plot wherever it's positive in green and negative in red. I take the imaginary component of psi and plot wherever it's positive in yellow and negative in blue. The central structure's cross-sectional area is proportional to psi norm squared, the Max-Born probability density. The volume inside any region tells you how likely you would find the particle there when you measured its position. Even though the initial wave packet dispersed, new wave packets will emerge and re-emerge periodically. Right now, a superposition of two wave packets travel in opposite directions. Their interference pattern produces the wave function's total shape. Notice how they follow two separate classical trajectories that pass right through each other, unperturbed by the other's existence. More wave packets will emerge as the simulation continues. You'll even notice a brief superposition of three wave packets if you look very carefully. Thus far, you have witnessed the solution to the time-dependent Schrödinger equation. This particular problem, confining a quantum particle to a line segment, is known as the infinite square well, which is used frequently when introducing quantum mechanics. Infinite square well solutions are periodic. This particular simulation repeats itself every 5 minutes and 26 seconds. Eventually, the original wave packet will re-emerge, which is known as phase revival. It will seem as though the original simulation is about to repeat itself right now, but actually, we are only at the halfway point. The original wave packet was traveling from left to right, but this wave packet at the equivalent moment travels from right to left. This packet is most compact but reversed at the halfway timestamp. There is still the other half of the simulation to go before we have completed one full loop. When solving relatively simple quantum mechanics problems such as the infinite square well, it would be very inefficient to use brute force numerical methods, such as time evolving the initial conditions forward a finite number of time steps. When solving partial differential equations, there are some very clever techniques available. Constructing this time-dependent Schrödinger equation solution involved using the standard separation of variables method. In a future video, I'll show you how this solution arises from that method. I'll show you eigenstate solutions to the time-independent Schrödinger equation, and we will evolve eigenstates in superposition to construct time-dependent solutions. We observe another superposition of two wave packets as we conclude 3/4 of the simulation. Much of quantum mechanics can be understood through linear algebra. The phase difference between these two wave packets is different from the wave packet phase difference after the first quarter. This is necessary because after another quarter, we must arrive back at the left to right wave packet and not the right to left packet. Some of you are familiar with linear algebra. I want you to think about the subspace spanned by two wave packets at the origin, one traveling right and the other left. These wave packets are almost orthogonal, so we can treat them as a basis for the subspace. The wave vector enters the subspace at the quarter points of the simulation. In the comments, I want you to construct a matrix acting on this subspace that is applied every quarter of the simulation. It must map the right traveling packet onto an equal superposition of both packets, which must then map onto the left traveling packet, which then maps onto a different superposition of both packets, which must then finally map back onto the original right traveling packet. We are now nearing the end of our simulation as phase revival takes place. Approaching one full loop, the original wave packet reemerges. Finally, the simulation is completed as the wave packet squeezes to its tightest. Then the next cycle begins. The wave packet starts dispersing again, and the infinite square well solution repeats itself ad infinitum. I hope you enjoyed this artistic quantum render. If so, please like and subscribe. I will be producing much more quantum mechanical content on this channel, so please stay tuned for what is to come.